In this lecture, we discuss isomorphism of elliptic curves. So say we start with an elliptic curve over K. So you get y square is equal to x cube plus ax plus b. This is in a short Weierstrass form. And then you consider change of constant. You set a1 as u4a, b1 as u6b, where you take from the algebraic closure of K. And this u should be non-zero. So this gives us a new elliptic curve, E1. And now let us say it is over algebraic closure of our original field K. So this new elliptic curve is y square is equal to x cube plus a1x plus b1. And the discriminant of this new curve, we set it as delta 1. This is u12 times delta. And this you can see immediately because this delta has only two parameters, a and b. So you take a cube and b square. These are the two ones which lie in delta. So you cube this, u4 you get u12, you square u6 you get u12, and that's precisely the one we are taking out. So now we are saying that these two elliptic curves E and E1 are isomorphic. So the isomorphism is in terms of morphism between algebraic varieties. So we have discussed a large number of examples of morphism of algebraic varieties in our lectures on algebraic geometry. So let us now see the morphism here. So now the morphism are from, this is from elliptic curve E to E1, but now we are working over the closure of the field K precisely because we have taken u from this closure. So you have in one direction the map is from xy, you take to u square x u cube y, and the other direction you go from E1 to E in this direction, and these are rational maps. And now you can clearly see that this phi and var phi are inverses of each other. Now this morphism, not only it preserves the points, it also preserves the group structure. So this map phi from E to E1, this preserves the group structure. So we have to show that this phi preserves the special point O, and it also preserves the group structure. So if P1, P2 and Q, they lie on the straight line, then phi of P1 plus phi of P2 plus phi of Q also lie on the straight line. So lying on the straight line meant this in the group law. P1 plus P2 plus Q lying on the straight line is O, then phi P1 plus phi P2 plus phi Q is O. So we use this O plus. This is the symbol we are using for addition of points on the elliptic curve. So here we are just writing plus. So if this holds that these 3 points are collinear, then this are also collinear. So this we have to show. So let us first focus on this part here. So phi of x, y, z in terms of projective coordinates will go to u square x, u cube y and z. Precisely this. Z we are not touching at all. So now for O, this our special point is 0 1 0. So this becomes u cube now. Now u cube is a non-zero element. You take it out. This again becomes 0 1 0, which is the special point of our elliptic curve E1 also. So this portion is done. Now you have to show collinearity. So on the elliptic curve E, on our original curve E, so this line L intersects E at 3 points, and we said that is always true because of Bezout's theorem. Now this line L is transformed to the line L1 because of a change of coordinates. So this ax plus by plus cz. So again now this line here, this is the line L. This line L will get transformed to this line, say L1. So again the same, instead of x we are writing u square x, instead of y we are writing u cube y. So this is again a line because this is a constant, this is a constant. So this line will intersect E1 again in 3 points, but the 3 points it will intersect E1 will be actually just the images of our original 3 points P1, P2 and Q. That is because we are mapping E to E1 by the same factor. So not only the line is getting transformed by the same factor, then you can see that the points are also getting transformed by the same factor. So the coordinates of the point are in x and y. So the mapping is also the same. So you do have this straight line getting transformed to this straight line. because the point of intersection is also getting transformed. So if two curves E and E1, they satisfy all these criteria, that is you have this transformation here A1 and B1 like this, your point is preserved, the special point is preserved, and then the point of intersection is preserved, this law is preserved, then these two curves are called isomorphic. And we have seen that they naturally satisfy this criteria if you just have these two conditions. A1 is U4A and B1 is U6B, and you have this mapping. So let us see some examples. So say we are given this curve E1, which is y square is equal to x cube plus x plus 1, and E2, which is y square is equal to x cube plus 16x plus 64. Then these two curves are isomorphic. So these two are isomorphic. You just take U as 2 over rationals. Now E1 and E3, these two curves, this is y square is equal to x cube plus 4x plus 8. These two are isomorphic, but now you take U as root 2. So you can immediately say root to the power of 4 is 4 here. And these are isomorphic over Q root 2. So this is root 2 added to it. So they are iso over this, but they are not iso. They are not iso over just the rationals. So they are not isomorphic over the rationals, but they are isomorphic over rationals you join root 2. Now we want a simple criteria to determine when are the two curves isomorphic. So the simple criterion to determine when two curves are isomorphic is the J invariant of the curve. So rather than going checking this, you can check the J invariant. So for an elliptic curve E like this, with the short wire transform, y square is equal to x cube plus ax plus b, and if discriminant you set it as minus 16 4a cube plus 27 b square, then this is the J invariant. This is minus 1728 4a cube over delta. Now if you plug this delta in, you can simplify this to 1728 by 4a cube divided by 4a cube plus 27 b square. So we cancel this negative sign with this negative sign. You took 4 square as 16 common outside, and you cancelled with this 16. So generally this denominator is referred to as delta rather than this entire term. Sometimes this is referred to as delta. So we are going to use this as delta in some places, and it will be clear from the context. So the big theorem is, so there are two elliptic curves. One is y square is equal to x cube plus ax plus b, and another one is E1, which is y square is equal to x cube plus a1x plus b1. These two curves are isomorphic if and only if their jth invariants are the same. So to show this, let us go in this direction first. So first you assume that the curves are isomorphic. If the curves are isomorphic, we have already seen that a1 is equal to u4 times a and b1 is equal to u6 times b. And then we also talked about how then the delta 1, that is discriminant of the curve E1, is equal to u12 times delta, which is discriminant of the curve E. And that is precisely again because you know the only variables are a cube and b square in the discriminant, and you cube this u4 you get 12, you square this u6 you get 12, and that's what you are taking out. So now we are writing the jth invariant of E1 like this. So this is 1728 over 4a1 cube over delta 1. So where now our delta we are taking as 4a cube plus 27b square. So now you plug this in. Instead of a1 you plug u4a, and instead of delta 1 you plug u12 delta. Now you cancel out u12, you get this term, and now this is the jth invariant of our curve E. So if the curves are isomorphic, you can see the jth invariants are the same. So notice that this is what we are using as the jth invariant. Now in the opposite direction. So opposite direction requires slightly more work. So first case is when j is not equal to 0 or 1728. Then you can say that this, you take this j, this value, and then subtract 1728 from both sides. So you take 1728 outside a common, and you have 4a cube minus delta over delta. This delta we are taking as 4a cube minus 27b square. So this negative sign comes from a negative here. You get 27b square over delta. Now you do a little algebra. You make this as j over j minus 1728. You get minus 4a cube over 27b square. This is what you get. Now we are going in the opposite direction. That is, we are saying that the j invariants are equal. So j invariant of our elliptic curve E is same as the j invariant of elliptic curve E1. So that would imply that, you know, for elliptic curve E you have something like this. For E1 you have A1 and B1. So you have equality here. So this comes from equality of the j invariants, because we are assuming now that the j invariants are the equal, and we have to show that the curves are isomorphic. So now you do the cancellations. Take a1 in the denominator here, a1 cube, and take this b square here. So you get a cube over a1 cube is equal to b square over b1 square. So now you set your u square as ab1 over a1b. So now you find out u4, you square this. So you have a over a1 square times b1 over b square. So this b1 over b square, you take this value and substitute this instead. So obviously you have to invert it. This comes right here, and do the cancellation. You get a1 over a. So you get a1 is equal to u4 times a. So our a1 is all set for isomorphism of curves. Now we have to just show the isomorphism for b1. So we have to show that b1 is equal to u6b. Then the curves would be isomorphic for our case 1. So similarly u6, now you put take this term, cube it, because this is u square, cube it, you get u6. Now for this part you keep it as such. For this part you see this and you substitute b square over b1 square. So you substitute this right here. Do the cancellation, you get b1b. So b1 is equal to b times u6, what we said before. So the curves are isomorphic. So now case 2, when the jth invariant is 0. So 0 is equal to 1728 over 4a cube divided by 4a cube plus 27b square. So now you can see that the numerator has to be 0. So a has to be 0. But this is 0 here, so b cannot be 0. So since a is 0, only thing we have to worry about in the isomorphism of these two curves, so these terms are not there, that these two should satisfy our law that b1 has to be equal to u6b. So you just take u6 as b1 over b. In the second case, if j is equal to 728, then you cancel these two out, so you get 1 here. So the numerator has to be equal to the denominator. So that is 4a cube has to be equal to 4a cube plus 27b square, and that will only happen if this part is 0. So that is the b's are the 0. So now a and a1 are non-zero, and to set them equal you have to use this. So now you set u4 as a1 over a. So we have been able to show that these two curves are isomorphic if and only if their jth invariants are the same. Now this j invariant, this is a one-dimensional space. Obviously it just consists of the real numbers, and this one-dimensional space parameterizes the elliptic curves. So you keep changing the jth invariant. So you keep changing your jth invariant, which looks like this. You keep getting a new elliptic curve. Every time you get a new j invariant, you get a new elliptic curve. So therefore this jth invariant is also called a coarse moduli space of elliptic curves. So jth invariant is a one-dimensional coarse moduli space. And what does it parameterize? It parameterizes the elliptic curves.